Okay, so now we can actually begin to describe the details of what's happening with this alkene reaction that we talked about 2 videos ago. And we're going to talk about what's happening between the ethene and the hydrogen bromide. So how are these two molecules interacting? The mechanism and the definition of a mechanism is actually a very important term to make sure that you understand, you have a good grasp. When I hear the word mechanism, is a step-by-step description of how we make and how we break bonds. Okay, so it's a step-by-step description. The reaction up above, this is just an overall reaction. And this overall reaction is going to be very different than what we're about to talk about, just the mechanism. And one way to describe the difference between the two is that, say, if you were to talk about Game of Thrones, an overall reaction would be you spending a few moments talking to your friend, setting up the characters, in the House Lannister. And then, you would spend maybe 30 seconds on this, and then you would skip 4 seasons or a couple of books into the future and just tell your friend how many of your favorite characters met with a grisly death. But when you do this, you're kind of skipping out on all the juicy details of what happens in between, the very beginning and a couple of seasons into the future or a couple of books into the future. So I guess in essence, what you would say is that, alkene reactions, the overall reaction, like what you see above, this gives the beginning and the ending. So you just skip to the end. But when you're skipping, you miss out on all these juicy details, character arcs, and internal motivations. So mechanisms are kind of like the nitty-gritty details of exactly how Tyrion Lannister would outwit all of his rivals and has somehow survived up to this point. So okay, so here are all of the nitty-gritty details for exactly how this reaction works. And mechanisms are really important because they give us insight into exactly the interactions that are going on. So let's go ahead and get going. So the mechanism for how this alkene reaction works is as follows. So we're going to start out with this alkene, and we'll go ahead and label this hydrogen in red so we can keep track of it towards the end. So the very first thing that happens with the alkene, or the ethene, and this HBr is not necessarily intuitive, but we're going to be able to, now that we talked about acid-base, nucleophile, electrophile, kind of give overarching categories for what's happening. And the first category or descriptor for what's happening is an acid-base reaction. So it turns out that the electrons in this double bond can work really well as a base. And so these electrons that are within the double bond can actually do this kind of motion, where what we're saying here is the beginning of the arrow is, again, electron starts, or where the electrons start, and the head of the arrow is where electrons end. And not only that, but we're also talking about bond making and bond breaking. So what we are really saying is that these electrons that used to be right here between these two purple carbons, these electrons are no longer going to be used for a double bond, and they're now going to be used to make a new bond between one of these two carbons and this red hydrogen. And so one mantra that we'll repeat over and over and over again is, if you make a bond, you must break a bond. There are some exceptions to that, but if you make a bond, you have to break a bond. So in this case, we've made a bond, and we also have to break a bond now. If we didn't actually break the bond, what we would see is that we would have a new bond between one of these carbons and hydrogen. And so this is our red hydrogen, and then this hydrogen still has a bond to the bromine. And now at this point, we can't really have this as a possible outcome, one, because, well, it's really weird to see hydrogen with a negative charge, but two, at this point, we've broken what's called the duet rule. So we should have heard about the duet rule at least once before, but hydrogen can not accommodate any more than 2 electrons in its valence shell. So right now we have 2 4 electrons, and that is exceeding the limit. So you can only have a total of 2. So this is actually no good. This isn't going to work. So this is not a possible outcome. Okay, so if we make a bond, we have to break a bond. So the bond that we must break now is between that hydrogen and this bromine. And again, the way that you would describe this mentally or verbally, if you were to dictate this to a friend or a classmate, is that the electrons that used to be between the hydrogen and the bromine, they're now going to the bromine. We're breaking this bond between the hydrogen and the bromine, and those electrons that used to be there are now on the bromine. Okay, this actually is going to work out pretty well, because if we talked about electronegativities, this hydrogen has a partial positive and this bromine has a partial negative. So overall, it's pretty easy to imagine this base abstracting a hydrogen, or the red hydrogen from HBr, because it is deficient in hydrogen. So go ahead and pause the video and see if you can predict the structure of the resulting molecule. Okay. So now that we've done this first action, we can go ahead and continue with the mechanism and redraw this molecule. So if we were to redraw this molecule, we have hydrogen, and let's just say we added it to carbon 1. So if we added it to carbon 1, we can draw the two implicit hydrogens that were originally on carbon 1, and we can also draw our final hydrogen. So this is our red hydrogen that we're adding. And then we can also talk about the implicit hydrogens that were on carbon 2 over here. So we started off with 2, so we must end up also with 2 hydrogens at the end of the day. So 2 hydrogens here. And I guess let me redraw the colors here. So really, these electrons that used to be between the 2 carbons, this is the purple bond, those purple electrons are now sitting between carbon 1 and hydrogen. So really, this should be purple. Okay, and so now we need to take care of charge and atom conservation across the reaction. So right now you can see the carbon 2 should have a positive charge. And if we have a positive, then we must have a negative to have charge conservation. So at this point, hopefully it's obvious that the mechanism is giving us a little bit more detail than just doing this overall reaction. We're getting more information about, at some point this carbon 2 is going to have a positive charge. That's really good information to know. Later on, that's going to be able to help us describe a lot of characteristics of this final molecule. Okay, but now what we have to do is we know where we're going. For mechanisms, it's great because you always know where you're going to end up, and we know we're going to end up with that bromine on carbon 2. So at this point, we can now try to designate one molecule and the other molecule as either nucleophile or electrophile. And so we can actually try to characterize one or both of these molecules as nucleophile and electrophile. So try to pause the video, try to categorize each of the molecule as nucleophile or electrophile before you move on. Okay, so now hopefully when you pause the video, it should have been obvious. I think that this is going to be your electrophile, and this bromine is going to be your nucleophile. So this was a pretty obvious choice because in this case our bromine was negatively charged and the carbon was positively charged. So we said before that the electrophile doesn't necessarily have to be positive and the nucleophile doesn't have to necessarily be negative, but in this case this is a very easy choice because of that fact. So now we've designated electrophile and nucleophile, and now you would have to remember, okay, nucleophile, what does the nucleophile do? What is the action of the nucleophile? And thinking back to the last video, you need to remember, okay, nucleophile is going to attack, and the electrophile is going to be attacked. And so this attacking action from the nucleophile, you always start the electrons at the base of an arrow, and you end the electron flow at the head of the arrow. So if you tried to draw the electron flow like this would be very bad, because the electron flow, you would then be saying, would start here, and that's not possible because this carbon with a positive charge doesn't have a lot of electrons to give. Okay, so that's no good. So what we would do, we would change the head of the arrow to the left, and then this arrow is perfectly acceptable and great and it looks beautiful, and then we can draw just like a little mini reaction arrow. And so after this arrow push, we could see we're starting electrons here, ending electrons here, nucleophile, electrophile, and we are now making a bond between this bromine and this carbon. And if we really wanted to be explicit about what's happening, we could maybe color some electrons green, and we could color all the other electrons white maybe, and we can show what's happening to form that new bond. So I'm just going to alter this arrow a tiny little bit and start them on the green electrons. So I'm going to start them here. So the electrons are going this way. And so that means at the end of the day, those green electrons are the ones that are making that new bromine to carbon bond right there. Okay. So overall, this is a 1-2 step mechanism, and this is something that you should be able to recreate if asked to do so. Okay. But again, this is what's happening for mechanisms. The mechanisms are the nitty-gritty details. It gives us a lot of information, and then the alkene reactions or the overall reactions just kind of skip to the end to give you, the final result of the reaction.